So I want to welcome everyone to REEF's third quarter webinar, Designing for Decarbonization. And to start us off, I want to point out that the task of transitioning away from hydrofluorocarbons, HFCs, requires a lot of groups to work together, from policymakers to building owner-operators, manufacturers, the service industry, many others. So it's really important that we understand the challenges and opportunities faced by all of those groups. And so for today, we're going to focus in on those faced by architects and engineers in buildings around system design. And I can guarantee you that no matter how you are coming to this topic, whether it's from climate and superpollutants, or HFC policy or building design, you will definitely learn something from our very experienced panelists. Next slide, please. So I'm happy to kick us off today. My name is Alicia Khan. I'm REEF's new Executive Director. And just a minute about us. REEF is a nonprofit collaborative organization. We work with a full spectrum of advocates and policymakers and industry in this space. And our mission is to inspire action by aggregating and amplifying the buyer's voice for solutions. So recognizing the need for by the end user, for the end user representation. And we're dedicated to finding solutions to eliminate the climate impact of refrigerants, and specifically the impact related to HVAC equipment, where we can find HFCs that can have 2,000 to 4,000 times the global warming impact of carbon dioxide. So to be clear, we're focused on reducing a key superpollutant at a time when greater access to cooling is a necessary response to extreme heat, and when expanding the installation of heat pumps is a critical part of electrification. So our strategy is to work alongside electrification efforts and decarbonization goals with a focus on accelerating the adoption of both lifecycle refrigerant management practices and also advancing technology solutions toward those that have zero climate and environmental impact. So this is our agenda for the hour, and before we get into the panel, I'll make some brief comments on the regulatory environment that architects and engineers are working within to put us all on the same page. Next slide, please. For those of you new to the Google Meet platform, you will find the little buttons in the bottom right-hand corner of your screen can be used to ask questions, and we hope that you submit questions during the course of the webinar. If you have a question in mind for a particular speaker, please go ahead and indicate that, or if it's just a general response that you're looking for, this will help us be more efficient with our time at the end of the webinar for Q&A. And also just to point out that everyone is muted, and we are recording this and we'll be posting this to the REEF website after the webinar. So let's do some quick table setting here on the refrigerants landscape. Basically, the point here is that refrigerants are everywhere, they're in everything, they're all around us, and they're also the fastest growing greenhouse gas globally. Next slide, please. So reducing the impact of refrigerants is really a global challenge, and to understand the scale of what we're talking about here on the left, we can see a look at how refrigerant use is projected to accelerate in air conditioning due to a rapid increase in cooling demand. And then on the right, the very extremely necessary deployment of heat pumps as we electrify our heating and cooling systems to get us off of fossil fuels. But as we support these critical efforts, we really need to do no harm, and that means reducing the global warming potential, or GWP, of the refrigerant gases that are used in this equipment, and which is going to sit there for the next 20 plus years. Next slide. So why is this a problem when refrigerants are contained within a system? It's a problem because leaks happen, and that's how they contribute to global warming. They leak or they're released. And this is a significant problem, and building operators know this because they pay to recharge their HVAC systems over the course of their lifetime. But adopting lifecycle refrigerant management practices, or LRM, can really address these problems. And with good LRM practices, along with effective investment in near zero GWP refrigerant solutions and other sustainable design options, we can get to a place where we're significantly reducing risks and costs for building owners. Next slide. So I want to take a second here and talk about the support for refrigerant transition in terms of policy. So we have global and national frameworks and other efforts in place to support the phase down of super polluting HFCs. Internationally, if you could go back, just thanks. Internationally, nearly 200 countries have committed to an 80 to 85% phase down of HFC production and consumption by signing onto the Kigali Amendment to the Montreal Protocol. And the US enabling legislation is in the American Innovation and Manufacturing, or AIM Act. This was signed into law in 2020 by President Trump, and it gives EPA the authority to phase down the use of HFCs and shift the market toward lower GWP alternatives. And I'll go into this just a little bit further on the next slide. But before that, I want to point out, if you could go back just one, thanks. I just want to point out also that there are numerous domestic regulations and codes and safety standards that support this. And a few of those are the Clean Air Act, Section 608, and that prohibits the knowing release of refrigerant during maintenance, service, repair, or disposal of air conditioning and refrigeration equipment. So this is about known leaks and intentional venting, making that illegal. This has been around a long time as it relates to older ozone depleting types of refrigerant that are no longer being manufactured. Another one is EPA SNAP, which stands for Significant New Alternatives Policy, and that lays out which refrigerants can be substituted for the types that are outlawed under the Montreal Protocol. And we also have ASHRAE best practice installation guidance, and this is referred to by architects and engineers and utilities. It's referred to in building codes and product certification standards, and is very useful for code authorities, insurance companies, and equipment manufacturers. Next slide. So just a little bit more about the AIM Act and how it works. Under the AIM Act, there are three legs of the stool, if you will, that are all really critical to work together to support a clear phase down of the production and consumption of HFCs by 85% in the US over the next 15 years. So the first part really addresses supply. So supply of high GWP refrigerants, it's aimed at chemical companies. In 2024, we saw a significant reduction in high GWP refrigerant production. By limiting new supply, we are going to really see an increase in demand for alternatives and reclaimed refrigerants. And the next big step down is 30% in 2029, and then there's one in 2034, and again in 2036. The second part is aimed at technology transition for new equipment. This requires the use of lower GWP refrigerants that have different safety classifications in this equipment. And then third, we have a focus on refrigerant management for existing equipment. So starting in 2029, it rolls out some requirements around leak detection and record keeping, reporting, and use of reclaimed refrigerant. I'll say if you want a deeper dive into this, REEF has a webinar on its site that I would recommend. It's on the California State Bill 1206, and Richie Carr from NRDC does a really fantastic job going into the policy in more detail and walks through it. So you can take a look at that. But ultimately, for today, all three of these regulatory or all of these regulatory pressures that I mentioned here and then on the previous slide are all reshaping the refrigerant market. And it's really important for us to be aware of what's coming so that we can plan ahead, and especially if you're thinking about building systems that are going to be operating for decades. Next slide. So just to wrap up, you know, it certainly begs the question that if there's all these benefits to managing refrigerants and looking at ultra low GWP refrigerant, so things like lowering your compliance risk, helping control costs, improving your operational performance, looking at, you know, GHG assets, refrigerants are becoming more visible when companies are looking at their assets for that, and then also meeting corporate goals around climate. Why isn't everyone doing this, and why are we talking about this still? Well, it's complicated. It takes different groups really working together and understanding their roles and the challenges and opportunities, whether it's owners or engineers or service providers, policymakers, or industry. And so that's why we're doing webinars like this, so we can really dig in. And I'm excited to introduce our panel, who will show you that we can do complicated things. And let me just get to my my cheat sheet here. There we go. So I'm going to turn it over in just a minute to Stet Sanborn. He's the Vice President and Director of Climate Impact at the Smith Group, and one of my wonderful board members at REEF. Impact is a national transdisciplinary team focused on performance, analytics, sustainability, climate resilience planning, and decarbonization at the Smith Group. Among a dizzying list of accomplishments and activities, including work on ASHRAE committees and supporting cities with electrification, Stet serves on the San Francisco Mayor's Decarbonization Task Force for New Construction, and he is joining us from the Bay Area in California. Second, we will have Rami Musa, who's a managing principal at Point Energy Innovations. Rami is an overachiever. I found him on a 2025 40 under 40 list, and he's been involved in some really exciting projects, including leading the rapid decarbonization of the American Institute of Architects headquarters renovation in Washington, D.C., where I am located, and new construction of the decarbonized operation of an international tech company and their 220,000 square foot office headquarters in Alameda, California. And he will also be joining us from San Francisco. And last but not least, we have Jamie Bacchus, who's Associate Principal in Building Performance at ME Engineers. Jamie is also an overachiever and has done it all, from sustainability consulting to energy modeling to policy work at state and federal levels. Jamie is past chair of the Lead Energy and Atmosphere, or EA, Technical Advisory Group, and he was named Lead Fellow by the USGBC, which is the highest level of achievement for professionals in the green building industry, and he'll be joining us from Denver. So Stat, I'm very happy to turn the mic over to you for the rest of the webinar.
Wonderful, thank you. And I do want to just encourage folks as we go through, because I know Jamie and Rami quite well, and we are energetic, festive folks. And I would encourage you to throw your questions into the Q&A. So just a reminder, it's in the little dots in the lower right-hand corner of your screen. Throw your questions in there, and they could be questions like, why is Jamie wearing a beard? But who knows? Like, we're ready to take whatever questions you have. These are topics that we, all three of us, are really passionate about. So please drop them in, and we'll hopefully have a really good conversation. It's a good sized group. So yeah, so with that, I'm gonna jump in and talk from a perspective of a design engineer and an architect, of like how to poke your team to reduce your long-term risk. This is really when you're designing projects. What are some things that you could do today to reduce the future risks that you might have on a project, or if you're going through project retrofits? And there's kind of a few buckets that I like to focus on. One, the first one is just right-sizing equipment. We have a historical trend amongst engineers to layer on safety factors and fear, and more safety factors and fear, to the point where our equipment might be twice the size that it actually needs to deliver the real load in buildings. And when we were doing combustion-based equipment, that cost delta wasn't that big. You could do that, and it wasn't that scary. And there wasn't a huge, there were some efficiency impacts, but it wasn't like this big deal. When we're moving to heat pumps, there's a lot of reasons we don't want to oversize our equipment. And that might be about refrigerant emissions, but it also might be about cost and getting your project to actually happen. So right size equipment, please poke your engineer, ask them, let's talk about how you're approaching the sizing of our equipment. We have a focus on trying to just reduce refrigerant runs in buildings, not doing refrigerant as a distribution medium for moving heat across an entire building. There's other ways that we'd love to do that. And not using refrigerant piping is a key way to reduce that likelihood of risk of leaks. We love, and I'll put a little, like if I have an emoji going on the screen, monoblock equipment, air to water heat pumps, water to water heat pumps, where all the refrigerant is contained within a piece of equipment. It's been factory sealed, factory tested. There aren't any refrigerant fittings. It just makes us happy because again, it's all about reducing that risk for emissions. Considering smaller equipment distributed instead of large central refrigerant-based equipment. And then one that's often overlooked is speccing inverter-driven heat pumps. When we do inverter-driven heat pumps where the fan is also controlled with an inverter drive, the refrigerant charge tends to be even less in that equipment versus single-stage or two-stage heat pumps. They don't have to flood the coil with wintertime peak load amounts of refrigerant, so they can actually right size the refrigerant within the system itself. So inverter driven equipment has a big impact on the actual charge volume of the system. So if you have to sign off right now and disappear into the world, I would say take this little this checklist with you and just apply it on every project. Next slide. So I briefly just want to talk about one of the things is we've historically not heard a lot of conversation about refrigerants, other than, is your total charge volume okay to meet a lead point? And everyone's like, great, I did that. I don't really know what they were talking about, but it seemed important. And we've focused a ton on operational carbon historically. What's your EUI? What's your carbon footprint of your operation? Are you grid tied? Are you doing PV? And it's really been within the last decade, and especially in the last 6 years, that we've taken a much more holistic view of whole life carbon. And so everything that it took to build your building, operate your building, and then end of life impacts of your building. And I want to talk a little bit about why that context has kind of set up this realization that we really do need to focus on refrigerants, especially because their impact shows up at multiple stages in the life of a building. Next. So if you haven't been sucked into the world of EN 15978, this is sort of the whole life carbon framework that we've borrowed from Europe and built on, but it's really looking at the impacts of all the stuff that goes into a building, whether it's the steel for the structure or concrete, mechanical equipment, you name it, all the stuff. How did we get those materials? How did they get manufactured, get adjusted, get put into a product? How did they get to our site? How did we use them? What was the energy use of our buildings? And again, what happens at the end of life? And we talk about these sort of zones of the whole life carbon as cradle to gate, gate to grave, or cradle to grave. And what kind of analysis you're doing just decides which portion of that lifespan you're studying. On the next slide, you'll see refrigerants pop up, as I mentioned, in a couple different stages of life. We tend to think of the consumption of refrigerants through leakage in the B1 category. So that's part of the use and maintenance of a building, just incremental leakage from small leaks or catastrophic leakage when a product actually fails. We think that as a consumptive refrigerant leak. But then at end of life, as we're taking a building down, that reclamation, as Alicia mentioned, not capturing that leakage or letting it vent out at end of life is a real big concern. So we see kind of these big impacts. On the next slide, though, your selection of refrigerants actually shows up in a lot of places or has an impact on a bunch of ancillary and related uses. So the refrigerant that you pick actually can have a really big impact on your energy use from an efficiency standpoint. Or if you're taking, say, a cooling tower and a chiller system and converting that to an air source heat pump, your refrigerant charge may go up, your cooling tower water use may go down. So there's relationships between all of these things, and that's part of that whole life cycle assessment, and why we want to stop making decisions as a single focused myopic analysis and start pulling out and making these whole life decisions where the total amount of impact from an environmental standpoint is reduced. Next. So I wanted to just share really quickly 2 examples to make sure I leave time for Rami and Jamie to chat. This is a recent project where, and I am showing only the MEP system. So this is a building stripped naked of its structure and its facade. These are just the pipes, the pumps, all the equipment on the MEP side, including the refrigerant piping, to show you that you can actually almost build a whole building with just mechanical equipment if you want. There's a ton of it there. But this is a study where we actually did a soup to nuts whole life cycle carbon as part of the MEP 2040 pilot project, where we studied every single component on the MEP system and its environmental impact. And this is for a built project that just opened. Next. Everybody always asks, well, or they're like, I'm not even sure how much carbon footprint all the stuff in my building is. So I just wanted to share for context that this is a breakdown of the MEP equipment from cradle to gate, that A1 to A3 category of all the equipment all the takeoffs from this project and the field weights. So lots in the mechanical equipment. Obviously, the PV array has a big footprint, but also offsets your energy use. But you can see the piping down at the bottom. That's the footprint of just the copper, just the materials in that refrigerant piping and our hydronic piping where it occurs. Next slide. The real thing, you could skip to the next one. The real thing, though, is starting to look at that use case. So from A4 all the way to C4, including operations. And I want to highlight the impact as we look at B1.2, which those are the leakage. Those are the assumed leakage that we're going to see in the lifespan of this building. This is a VRF building, lots of refrigerant piping, lots of field connections, lots of opportunity for future leaks, just because from a quality control standpoint, a very efficient system, gets us all the EA points. We're like, rah, rah, rah. But as we step up and look at the whole life impact, we realize that the potential fugitive emissions from refrigerant leakage actually may dwarf some of those savings that we are seeing on the energy use standpoint. I just want to point out that we had to truncate the graph. So the B1.2 on the far left actually goes up far higher, but we had to trim it off so that we could get all the values onto a single chart. But if you look at the actual hard values, there's an order of magnitude shift in the impact of the refrigerant emissions versus B6, which is the operational carbon footprint of the energy on the project. Next slide. One of the key things that you can do as a designer is actually just specify lower embodied carbon or lower GWP refrigerants. So this is a comparison if we had been able to do the same system going from R410A, which was originally specified and built in the project, down to R32, which is one of the sort of newer class of A2Ls, mildly flammable refrigerants, and then going to 454B, which also has a slightly decreased GWP. But I do want to just highlight for my friends in the A3 world, if you look all the way to the right, you might miss it. That's the beautiful propane. If we were safely able to convert this building over to using R290, you can just see that dramatic drop. Now, would I do R290 in the VRF system? We'll talk about that at a later time. But I just want to show you that actually just specifying refrigerant can have a dramatic impact, even using the same system typology. Next. So here, looking at the whole life of all the MEP systems, you can just see that the refrigerant emissions still dwarfs all the other components from a whole life carbon standpoint in the building. And on the next slide, you'll see those same results actually now, because this is one of the first projects that we've done as a firm where we've done the entire MEP system, the entire structural system, the entire enclosure, all the landscaping components, and all the civil earthwork. So this is our most comprehensive analysis of all the effort that it took to build up this project, and showing the relative impact of emissions on the whole lifespan. Emissions from refrigerants are still the largest contributor to whole life carbon or whole life emissions for this project. Even MEP dwarfs structure in this case for our study. Next. So I want to, other than that terrifying note that emissions ruin everything that you've been working for your entire career, I do want to give a case of hope from a design standpoint. So this is a really quick case study of a project that we're doing up at Cal Poly Humboldt. Next slide. where we ask ourselves, instead of specifying quote unquote the right size piece of equipment to meet the load, what if we designed a system that was too small and we added some storage? Next slide. People don't realize that the peak load that's seen in a building actually only occurs for a very short period of time, depending on what climate zone and use type you have. But there's an opportunity to not put in a huge piece of equipment just to do a tiny little bit of work. So adding thermal storage on the next slide, we can start to see the benefits of thinking about undersizing equipment paired with storage to match loads. This is the lifespan emissions from a project, from that example project. For embodied carbon of the equipment, just the mechanical plant equipment plus refrigerant emissions, using R410A. On the next one, you can see the benefit of going to a low GWP refrigerant. So in this case, R454B. Next slide. That's roughly an 80% reduction in whole life impact, just making that refrigerant change, which is really substantial. And then on the next slide, and you can click immediately to the next one, you'll see that undersizing the equipment by half using thermal storage to meet your peak loads, now we can achieve almost a 90% reduction. So there are opportunities from a design side to actually be able to make pretty effective change. So with that, I think that was just a summary. Try to design, reduce your peaks, make a more efficient building, try to specify equipment that doesn't have refrigerants. And then if you are using refrigerants, consider smaller equipment with storage, or at least at a minimum specifying lower GWP refrigerants. So with that, I think I'm going to hand it over to Rami to help you develop a plan.
Thanks, Ted. Good afternoon, everyone. I'm excited to have you all here with us. If we can go to the next slide here. I guess just to start off, thank you all for being here. Refrigerant and just talking about refrigerants has historically been a very niche subject, right? Whether it's the design community, ownership and operation, it's typically been whatever is available and whatever is allowed is what gets used in equipment. Maybe there's an investigation into what's most efficient, great. And even that is a sort of subset of the community. So, I mean, harmful refrigerants have been used for decades up until now. And fortunately, those are being slowly phased out. Phasing out old refrigerants and phasing in is becoming more rapid recognition of how harmful these really can be. And with synthetic chemical refrigerants, the elevated GWPs that we see really need to get a handle around that. So in 2020, we set course for the phase out of some really prominent refrigerants. HFCs would be their classification, like R410A, R134A. Those are common numerics that we see in equipment and have for the last decade. And they were commonly used all the way up until last year, where access to this refrigerant now, very soon over the next 20 years, will be dramatically reduced. In 2025, there's a critical landmark phasing in the next wave of lower GWP, lower impact refrigerants, where only this type can now be used in new equipment as well as imported equipment. So why should you care, attendees? Heating and cooling systems with lifespans of 10 to 35 years were being designed and installed with these more harmful refrigerants until just last year. And though it's a relatively slow process, these systems will inevitably leak and require replenishment, often as much as half to 3/4 of their initial refrigerant charge over the course of their life. So if we can jump to the next slide here, with the most recent phase out, R22, which just hard stop, cannot be produced any further starting in 2020, we've seen almost a 10x increase in unit cost for that refrigerant. So replenishment of these refrigerants that are now being phased out is going to become a significant part of the operating expense for a building. We can't let that slide. We can't ignore that impact. Next slide, please. As we mentioned, over the next 20 years, Alicia alluded to this phase down of HFCs again, like 410A, 134A. Over that course of 20 years, though, there are some distinct jumps in reduced or in phasing down of production. One in about 4 years and another in about 9 years. And so these phase downs are very likely to trigger increases in cost due to supply and demand impacts of that phase down. So although we're thinking long term here, there are much more near term impacts to buildings and operators as this equipment that may have been installed last year is in operation. Next slide, please. So, what's more, refrigerants are now in higher demand than ever before. Governing policies continue to evolve to address issues of climate change. And so there are the refrigerant phase outs, like the one we're talking about now, but perhaps most pressing is the need to electrify heating sources. And this has put the most pressure on manufacturers and their heat pump refrigeration products. Embodied carbon policy is also in the works. This is in its infancy. It's being established just a few years ago in California, but also in Washington State. They don't include refrigerants yet, but they will very likely in future iterations. So these are all policies that are coming together to really dictate what we can and can't install as designers and where we should be advising our owner and our clients. Next slide, please. So what can we do about it? This sounds like a lot, and I can't say we have all the answers, but there are things that we can do now to prepare and reduce risk with these refrigerant transitions. So we've talked a lot about how great an impact refrigerants are, but I first want to just emphasize that building electrification and shifting to the use of refrigerants in lieu of combustion is still a far better source or case for the world, less harmful than continuing to use those combustion and fossil fuel based sources. Refrigerant emission impacts, unfortunately, just are not being considered as critically as they should be by many in the industry on both the design and building operators side. So they've been a bit like that sneaky monster under the bed that nobody really wants to look at, and we just kind of run with what manufacturers give us. So how do we really start with assessing this risk? And the first step is just understanding, what do you own and how much? Where is this refrigerant and what type is it? That will dictate, how challenging it may be to come by in the near future, and how much of a risk it should be contributed to that. We need to identify where the equipment is with the greatest consumption and where are the greatest opportunities to improve and reduce refrigerant consumption by monitoring. Whether it's recharge or actually having a clear picture of that history, creating a register of that use. Many property managers, this isn't quite on the radar yet. It's been just a minor operating expense. So we want to keep this in clear, eyes wide open as we go forward. When we're installing new systems or considering retrofitting existing systems, we really need to consider the full life cycle cost. I think there was a question, actually a great one, that we'll touch on a little bit here, and Jamie will get into as well, about how do we include refrigeration cost and escalation in our life cycle analyses for cost, for operating cost of the building. That's got to make its way in, and oftentimes is neglected in life cycle analyses. And for the assets that remain with these older refrigerants in the years to come, where will you gain as an owner the best value? Is it in banking that phased out refrigerant to be able to continue operating it until that equipment needs to be replaced? Or do we simply replace that piece of equipment with something new that is compatible with lower GWP refrigerants? These are assessments that can help us develop a plan and reduce the risk of cost escalation uncontrolled going forward in our capital planning efforts. Next slide, please. So as I mentioned, it was just earlier this year where this new wave of low GWP refrigerant has been required. It's just now being applied and installed. And as we've done that with this new wave of lower GWP equipment, there have been some lessons learned, and want to share that with you all. And really, we need to share as an industry more to adapt to these rapid changes as much as possible. So first, when we were investigating what are these new products, what can we apply, we did a market survey of 10 of the most prominent heat pump manufacturers with this new wave of refrigerants, whether R32 or 454B. And honestly, none had their full equipment lineup available to ship on day one of this transition. And that is very likely to be the case going forward. So we need to be aware of what is the most realistic lead time for the applications we have at hand. Is it a large package unit, which may be farther out on the development timeline and less common? Manufacturers don't prioritize it. Or where is the availability for the type of equipment we need during these transitions? Another consideration here is that highly technical and test data for every operating condition that we need to make thoughtful, prudent design decisions for this new equipment won't be available on day one either. So we need to ask the right questions. Getting into really some significant details that we don't think about until later, like equipment staging and part load operating conditions and temperatures. How does the system react to those conditions? That won't be published on day one, most likely. We also need to very rapidly get up to speed with new equipment. So seeking out training from manufacturers reps, or seminars like these can help us as an industry get up to speed more quickly and make, again, informed design decisions so that we don't have catastrophic failures or sunk cost when applying this new equipment. Additionally, this is new equipment for everyone. So with the technicians, manufacturers, they are going to have growing pains as these new products are being applied. And we've got to account for that in our startup scheduling and in the support or the planning efforts for commissioning of this equipment. And lastly here, these are not the historic boiler systems that just kind of run and we don't think about and we just look at bills. We need to really be conscious about how are these equipment operating. We need to monitor them to get the best value out of them. So having the correct instrumentation and ideally a monitoring-based commissioning plan, especially for larger systems, so that the system can operate as intended and continue to after the first year or two of operation. Next slide, please. Okay, so what can you do after this session? Everyone has a part to play in this and can be proactive about this adaptation and transition. Owners, facility managers, start assessing the risks that we're discussing in this session. There are things that we can do to prevent surprises in the future and make some proactive plans. Manufacturers, really, we need your help to allow owners and design teams future flexibility with equipment and not have planned obsolescence of equipment that we know will not be able to be supported in less than a decade or will be far more expensive to do so. So having some proactive plan within products for these future, everybody hates the word drop-in refrigerants, but what are changes that can be made without complete equipment overhauls or replacement? And although engineers need to really take the reins and take the lead on educating clients, architects are not off the hook. We've got to make sure our owners are aware of these risks and can make perhaps the investment in looking at things a little bit more deeply than the conventional, what is the operating energy cost only to dictate ROI, something to that effect. And again, engineers, really, we need to ensure that these risks we're talking about today have sufficient guardrails for successful product applications in our projects. This is new equipment, again, for everyone in the industry. And we have to acknowledge that. It can't just be business as usual, as it has been for decades. Next slide, please. And lastly, just want to wrap it up here with a positive note that this stuff can be done. There are products out there being developed, being tested. This is one particular application where I sit on an advisory board for a CEC grant application. This is a CO2, so carbon dioxide refrigerant heat pump. So it is extracting air from the heat from the air around it and pulling that into the heated water that's supplied to a building. CO2, global warming potential of 1. It is a commercially available refrigerant, R744. And again, it actually, another piece we're not talking about too in depth today, but it is not a forever chemical. It's not PFAS. So it is even more beneficial. The list kind of goes on with the opportunities with CO2, and this is just a technology that is being adopted by the HVAC industry very recently, like last year recently. So exciting to see these this type of technology grow and become a bit more prominent. Okay, thank you.
So Jamie's up. Yeah.
Oh, we can't hear you, Jamie.
Yeah, no sound yet, but we do accept interpretive mime, which I do think Jamie's actually quite good at. As Jamie, I think is going to try to call in and get the sound going. I do want to encourage everyone again to go into the Q&A. Feel free to enter your questions in there. You'll also notice on the far right-hand side, there's a chance for you to upvote any of the questions that you're like, oh, that's a great question. I wish I would have asked that. I really want to make sure that they cover that. So this is just a chance to hop over into that Q&A and make sure that we, when we do get the back and forth, we get a chance to answer some of the questions that you're dying to ask.
Stet, do you want to take one of those questions while we're waiting for Jamie
Sure.
to rejoin?
Yeah, happy to. I can kind of take them in order from highest upvote. I know the first one is actually one for my the leakage that was assumed in the study that we were doing. Those were per ASHRAE 228 leakage rates. So there's a whole range of leakage rates assumed for different equipment type, everywhere from 1% to, in catastrophic cases, 12% per year, depending on system types and age of equipment and use patterns. But there is an ASHRAE study coming up soon that's going to take a really deep dive into very large portfolio scale leakage data. So we should be getting better refinements on real life examples soon. Still no sound, Jamie? Do you want to do a sound check? Oh. I'm not sure, but I can definitely take another couple questions as we try to get Jamie. Oh, for Jamie's call-in, Jamie Mitchell, I'm not sure if you can allow his call-in person to be a contributor, or else he's automatically muted.
I will do my best while you answer the next Q&A.
Okay, sounds great. As we work on that, oh, the upvote. Okay, so what about VRF? I'm going to throw this one to Rami. I'd love to, because I have some feelings about it. but Rami, I'd love to hear, because you guys do a lot of work with clients, advising them on strategies around system selections. What are you guys saying these days around risks around VRF?
Yeah, VRF is definitely a hot topic and a challenge with managing refrigerant volumes. There's no way around the quantity of volume that is used in VRF systems. As historically applied, there are some interesting adaptations of VRF to reduce refrigerant where they're actually hybrid. They are partially hydronic and partially refrigerant distribution, where essentially the main riser would be refrigerant, and that would then tap into what would be the branch selector, or whatever we want to call the box, the refrigerant header and distribution center. That actually transitions to water. And so all of that distribution downstream of the riser could then be 0 GWP. So that's one kind of adaptation or upcoming change. There are efforts to also not necessarily retrofit, but develop the VRF systems now with lower GWP refrigerants. So R32 is being applied in one particular case, but the manufacturers are more slowly adapting, unfortunately, and are giving the leeway to more slowly adapt to those changes.
Yeah, I'll definitely say that with the code requirements around refrigerant and space allowance and charge within spaces, VRF will continue to continue to be a challenge. But Rami's totally right. The hybrid units definitely give you a pathway towards still getting really high efficiency without the push on the total refrigerant charge. A great question is, what do I do with all the systems I already have? I'll throw in to echo what Rami said earlier. This is the time to actually understand what you have and get a full inventory of the systems that you have, and what some of the potential options for doing end-of-life replacements or preemptive before equipment fails replacements, because it's a huge challenge. Most of the new refrigerants are not drop-in replacements for existing systems.
Yeah, but like we said, we certainly don't have all the answers, and manufacturers really need to step up to ensure that these do not become stranded assets, and that different refrigerants can be used within these future systems. So this is something that the industry is certainly pressuring VRF manufacturers on.
Yep.
Sorry, Jamie.
They'll know Jamie's sound. We'll keep going through questions and just see if there's a potential connection. So to the anonymous question on, can I just swap out refrigerants I have in my system? For most cases, no. The new requirements for leak detection in A2Ls from a safety standpoint, and even just the performance of those refrigerants, what the compressor and the coil size and the pressures that they operate at, they tend to be different. And so, as Rami mentioned, most of these systems that are legacy do not have a drop-in refrigerant swap out that you can just do and move on your merry way. So a lot of it is putting a plan in place over time that you're going to do a replacement, and that whole life cycle cost of the cost of refrigerants over time as it goes up for some of these assets. It's a great time to put a plan to how you're going to transition. We'll try again to Jamie version 2.
Looks like you're muted on your other device.
I'm on like
There you are.
Devices.
There you are. We hear you. So with that, I will love to hand over to Jamie.
All right. So next slide. I should have kept the beard on. All right. So we have all these refrigerants, and they have a global warming potential. And we talk about them in CO2 equivalents. And we can talk about them in 20-year potentials or 100-year potentials. And most of us have probably been talking about 100-year global warming potential equivalents without mentioning that or referencing it, but realize there are two different ways. And it's the radiative forcing equivalent of these gases. And if you're really interested in pushing or promoting or showing the impact of refrigerant leakage on greenhouse gas effects, you would use 20-year, because some of these are really short-lived once they're released into the atmosphere. And so we might be thousands in the 100-year time frame, but multiply that in 20-year time frame. Next slide. And so we touched on this a little bit earlier. We have emissions from buildings that are scope 1 when you burn fossil fuels, but refrigerant leakage is also a scope 1. And then your electricity, if you have district chilled water, heating, hot water, steam, that's a scope 2. And scope 3 is kind of everybody else's stuff. Next slide. And then taking that, overlaying it with the EN 15978, as Stet was saying, we have B1.2 that we think of fugitive leakage emissions, and C as the end of life. But you have, as Rami said, this equipment lasts 10 years, 15, 20, 35. So you have multiple replacements over, let's say, a 60-year typical life of a building. And then all these have interrelations with the energy and the water use. Next slide. So there's a couple new ASHRAE standards that are to consider that are quite exciting. ASHRAE standard 228 that came out 2 summers ago looks at net zero carbon for existing or new construction buildings, but it only looks at 1 year. That's it. So you don't get that end of life. You just get, what were your leakage this year? And so it's a little narrow. 240p looks at a 60-year reference study period and the leakage that occurred during installation over the course of that 60 years, and then at the end, which is again that C1 next phase. Next slide. So there's some tools, which is great, because we don't want you to leave this without thinking that you're on your own. SIPC came out with technical memorandum a few years ago, and they made a North American version with ASHRAE that recently came out. So this is great. We have a new resource that sort of looks at refrigerant leakage and the MEP carbon that Stet was also showing for all of our systems as mechanical engineers, electrical engineers, plumbing engineers. MEP 2040 also came out recently, this past June maybe, of a free embodied carbon guide for beginners. You have to pay ASHRAE for theirs, but this one's free to download. C-Scale is also a free tool to use. Next slide. And so back to those 20 and 100-year GWPs, this gives an idea of the difference. So if you were looking at R410A and you were thinking it was around 2000-ish, well, it's in 100-year GWPs, yes, but if it's almost double if you look at it in a 20-year, because it's a very short-lived greenhouse gas. And the top rows are the different IPCC reports. So AR6 is newer and slightly different than AR4 or 5, but they shift very little. So don't get caught up on memorizing these. If somebody says R410A is 2088. That's because they're using something from a decade ago, but it's still relevant. All right, next slide. One of the things that you also have to kind of consider when you're designing systems is, and the quantity of the refrigerants, are they centralized or are they decentralized? And if they leak, where would they leak? So we can get into this on the next slide, but it is something to consider. Somebody asked in the chat about what leakage rates you were assuming. And it's almost anyone's guess. 228 ASHRAE standard, that is, will only give you the annual leakage. ASHRAE's 240P will have an installation, annual, and end of life. And so we have these various things from California Resources Board, we have them from Australia, we have them from the UK, and we have them from LEED. They all sort of disagree, but are close-ish. And this is a problem for our industry, that we have piecemeal studies that are done on a specific type of equipment in a specific region at a moment in time that may have been CFCs. And then somebody else may have studied something in the 90s and early aughts that was HCFCs. And now we're looking at, as Rami said, HFCs. And so can you extrapolate some of these lower pressure system leakage rates with higher pressure? Hard to say. And different construction practices. And even if you look at 228, it's using a French study, and their description of a DX equipment is not necessarily what we would think of as that same DX equipment. So don't lose hope, but realize the citations behind the data are lacking. And we collectively need to do better. Whether it's ASHRAE, ULI, BIPSA, we need to better understand this. Next slide. And so real quick, if you're just doing some refrigerant calcs, you might have, as we were seeing, for factory charged equipment, maybe 0 leakage in the first year, or 1 to 2% in that initial, and then something 1%, 5% per annum, and then something assumed at the end that you still might have 80 to 100% of the refrigerant charge left, and then you're able to reclaim 70 to 90% of that. And so you can then, and then you have the service life. And so you can then just easily plot those of just like, okay, so I lost 1% of my refrigerant charge, and then 7% per annum, and 17 years later, 80%. So that's what these numbers are coming from, and how you would add them up. Next slide. And that's what it graphically looked like just every year for different types of systems. And next slide. And so this is what it looks like cumulatively. A giant question for all of us is that after that bump up, do you reinstall the same refrigerant or something that's now 0 GWP? And so that could just plateau, because now you've moved on to something with natural refrigerants and has 0 GWP. Next slide. And this is no surprise. If you assume VRF has 4 to 6 pounds of refrigerant charge per cooling ton and has the highest leakage rates, it's going to look the worst. Whereas if you assume you have packaged rooftop units with only 1 or 2 pounds of refrigerant charge per cooling ton, and they are factory charged, don't have any initial leakage, and then a slower over their life, they'll look better. The weird part to keep in mind is that if you have centralized systems and you suddenly make them 100% redundant, then you just double the refrigerant charge of that system. But it's probably in a refrigerant machinery room, and so the leakage less, and it's more controlled because you have all of the requirements for that. Next slide. And again, as Stet was saying, this is only a small part of the big picture, but it's an important part. Yeah. Next slide.
Well, and Jamie, I might pause you here just because we're at the top of the hour.
I know.
But if you would have one closing statement to charge and go forth with of hope and inspiration, what would it be?
I think the good news is with the AIM Act and the global consensus around Kigali is that we are moving past this. The challenge is what happens with all this stuff that we've already installed over the past decade. And
how about you, Rob? Yeah,
that's our own albatross for all of us that did these early VRF systems or even just packaged rooftop units. The good news is for the simple systems, they just pull it off.
Yeah.
And reclaim it because it's going to be worth something to somebody else.
Yep. And Rami, any big closing thoughts to charge folks out with?
Yeah, I think one area of hope, I suppose, is that cooling systems in large part have had low GWP refrigerants available now for years. HFOs are becoming pretty common in large refrigeration equipment for cooling. Heating is one area where we have the most challenge and most nuanced design considerations. So as we move forward towards more electrification within buildings, we need to build up our familiarity with operating regimes for heat pumps and how we can best, as you touched on, Stet, right size, and how do we get to the best value system that has the lowest environmental impact.
And I'll just close us out with, we're in the Wild West right now with the transition, with equipment replacements, with refrigerants in a phase down. But you're not alone. We wanted to share these resources with you. Jamie mentioned it as well, but the MEP 2040 group is a group that's obsessed with, on the practice side of designing and engineering to try to reduce total emissions. The project that I showcased was actually one of our pilot projects with MEP 2040. So you can do a deep dive there. Both SIPSI and ASHRAE have a ton of resources that have come out in the last year and will continue to come out with additional resources for designers, for engineers to target strategies to reduce those emissions, especially on the design side. So with that, I think I can hand it off over to Alicia for the final wrap up for REEF. If not, if you have any questions for REEF, we have our contact email and a QR code there. We're always looking for volunteers to join our meetings, speakers, and partner organizations that are allied along with REEF's mission to reduce fugitive emissions, emissions at end of life. So please reach out because we would love to partner on initiatives and outreach.
Thanks, Stet. And I'm sorry I couldn't get off of get my video on and get off of mute. I really want to thank all of you for your time and energy to put this webinar together for everyone. It was really fascinating and so much more good information, I think, to come. I do want to say that the questions are fantastic in the chat, and we really do want to answer them. And like Stet said, help you feel like you're not alone, because you're not. So we will be collecting those. We will get answers to all of them, and we will post them in a blog on our REEF's LinkedIn site, and we will make sure that we share that all with you so that you see it when it's posted. So again, thank you so much. Really appreciate it. Have a great rest of your day.
Thanks, everyone.
Thank you.